This video is based off of a 2009 paper by J M Gibson called The Birth of Blues: How Physics Underlies Music. Pythagoras is credited with creating the musical scales we use today. He used his intuition to guide the creation of a popular musical creation aid called the circle of fifths, which is, in some ways, derived in the same way that mathematical axioms are. Pythagoras took a string on an ancient instrument called a monochord and divided it into different ratios between the two halves of the string. From these ratios, scales were developed, and from the scales, rules about harmony were developed. Mathematical axioms, or statements about what is self-evidently true, are built by extracting as many logical consequences from a situation as possible. Like math, music creates axioms, or rules based on aesthetic logical consequences. The differences in the ways to tune a stringed instrument are sometimes only different by 1%, more or less. Still, surprisingly, humans can tell the difference. We have an intuition for what is pleasing, and it coincides with certain frequencies. So, pleasing music isn't always subjective. Let's follow a string on a musical instrument. We're particularly interested in the way strings have frequencies when plucked, because the frequencies determine harmony, and harmony and melody are closely related. Frequency determines pitch. Rhythm is also related to frequency, because rhythm is related to resonance, and resonance is related to frequency. There are three main, simple, beautiful harmonies: unisons, identical notes, octaves, and perfect fifths. When one string is plucked with another string of the same fundamental frequency, omega, such that there is a 2:3 ratio between the pitches, the harmonic interval is called a perfect fifth. An octave is either double or half the wave of another wave. Strings with frequencies omega and 3 omega also sound harmonic. If we take 3 omega and bring it down an octave by dividing by 2, doing this keeps the note in the same octave as the previous note, then we have the interval 3 omega over 2. The ratio 3 over 2 is considered the perfect fifth, one of the fundamental beautiful harmonies. Pythagoras divided his monochord string with a movable bridge and discovered that two strings with the same tension and ratios like this, and others, were harmonious. Pythagoras started with the note F and used the perfect fifth to derive the other 6 notes in the 7-note scale. 7 notes allow for 2 octaves in his system of dividing strings. In terms of frequency rather than just string length, there are 2 different types of steps between notes: tones and semitones. There are errors in the Pythagorean system, especially when going above 12 notes. The Pythagorean comma is a major imperfection in Pythagoras' system of dividing notes. The pentatonic scale is generated by taking the first 5 notes generated through perfect fifths: C, G, D, A, E, or arranged C, D, E, G, A. Many people in many cultures find the pentatonic scale more pleasing than the traditional Pythagorean one. For centuries, musicians debated about how to compensate for imperfections in tuning, because there's no perfect way to divide the strings and get exactly the desired frequencies and harmonies. Pythagorean and just tuning, or tuning according to perfect integer ratios, will result in having to retune the instrument if you want to change keys. Eventually, someone named Werkmeister invented a robust way to tune an instrument so that it sounds in tune when playing in any key. This is thanks to the invention of logarithms in the 1600s. Modulation, or temporarily changing keys in a piece, is a method used by musicians like Bach to add more complexity to musical pieces. This wouldn't be possible without this new way to tune instruments called equal temperament. Gibson's paper says that, quote, "Harmony and scales are chosen because they form a closed set of relationships. Underlying simplicity and symmetry is the origin of the favored musical scales." This is true, and although people enjoy sounds based on logical principles, music is also infused with tradition, and people often prefer mistakes that are nostalgic. Academic papers need to establish the usefulness of their research in order to pass peer reviews. Gibson concludes and establishes relevancy by pointing out that music is a great way to teach students about frequency and other topics in physics like quantum mechanics. You can use music to teach quantum mechanics like this. Our ability to hear different pitches is directly related to the Fourier uncertainty principle, and uncertainty principles are very important in quantum mechanics, mainly Heisenberg's uncertainty principle. So there are similar principles. You can't have both precise time and precise velocity in either Fourier's or one version of Heisenberg's uncertainty principles. But unlike measuring subatomic particles, you can hear music and have a sense of intuition about it. This video is based off of a paper by J M Gibson called The Birth of Blues: How Physics Underlies Music. There's an accompanying 1-hour public lecture you can request if you submit an email with the subject Physics of the Blues to this email address. If you liked this video and want to see more, please click like and subscribe, and click the bell to receive notifications every time the Physics Librarian channel uploads. You can also share this video and see who else in your social network likes physics, or start a conversation by leaving a comment down below. Thanks for watching, and I hope you'll be back soon.